So, how do we approximate the solution of P0 epsilon? Let's discuss several pursuit algorithms relying on the OMP and the basis pursuit, which we have already met. Recall the OMP algorithm, which was designed to approximate the solution of the P0 problem. It is initialized by a zero solution and an empty support, and adds one non-zero at a time to the solution. This is done by first choosing which atom to add, taking the most correlated atom to the residual. Then the solution is updated along with the residual. At each stage, we check the energy of the residual, and if it is below some threshold, we stop the algorithm. Well, this very algorithm could serve for handling P0 epsilon with hardly any change. When moving to the P0 epsilon problem, stopping the algorithm when the residual L2 norm is below epsilon is all that we need, and the resulting OMP is now serving our new goal. Indeed, when it comes to approximating the P0 epsilon problem, the OMP we have already studied keeps all its properties. These include the fact that it never chooses the same atom twice, getting an orthogonality of the residual to the already chosen atoms. The OMP retains its computational complexity and the relevance of the numerical shortcuts we have discussed. In fact, all the greedy algorithms could be adapted to handle the P0 epsilon problem in the very same fashion. And all that it takes is to modify the stopping criterion. What about the basis pursuit? Well, starting from P0 epsilon, the core idea of the basis pursuit was to replace the L0 by an L1 norm. Thus, here is the basis pursuit for our case, a problem we shall refer to as P1 epsilon. This problem is convex, and thus far more comfortable to work with. Note, however, that this problem cannot be cast in a linear programming form. It is related to a more challenging problem known as quadratic programming.